Hello everyone, this is Arip Nur from Group 10. I would like to introduce about our project 2, linear programming of analysis of material recovery facilities. The topic was chosen in recognize of how it demonstrates the feasibility, advantages, and challenges of linear programming in analyzing optimization problem in engineering. The feasibility of this optimization method is demonstrated in several reference studies as well as in the Central Material Recovery Facilities or CMRF cited paper from Lund et al. 1994. By addressing how linear programming should be used as a preliminary tool for guiding the potential direction for CMRF, it demonstrates part of its challenges. Several studies have shown that linear programming can be applied to civil engineering or related problems. For example, to model the benefit and limitation of water distribution network leak detection, or modeling the minimizing the cost and ready-mix concrete transportation problems. Another case about maximize the probability of trapezoidal channel capacity being greater than design flow and minimize probable costs of the channel. Another paper showed that canal irrigation scheduling using mixed integer program involving outlet flow duration and target flow start time. Also, level and resources of highway reconstruction project that was planned and scheduled using an integer linear programming formulation. Problem statement. The design and operation of central material recovery facility is confronted with various alternatives and constraints. These alternatives include what percent of landfill disposal and what physical and logistical constraint will constitute least cost design for CMRF. The decision on which alternative is optimal regarding cost and quantity of recyclable and landfill disposal can be aided by linear programming, combined with conventional engineering process for flow diagrams and comma-separated value spreadsheets. Numerical or analytical methods for identifying the optimal solution are developed for designing at a least cost operation of solid waste utility.
Hello, my name is Negar Saraei, and according to the equation, we try to find the components and variables based on the equation 1 to 9, and there are some components and variables which are really important. And for the first equation, as you can see, we have the CF and also some variables named PL, LK, and PLS. At the first level, we defined them and we determined the description and we made Excel for them. And to have the just quick description, the PLK is the cost of labor, and also we have the revenue for the PSIR to RTSI. And we have another variable which is like very important, and is DI and DT. DI is a total waste diversion, refers to the purpose of diverting waste away from disposal, but the DT is the daily quantity of waste disposed of the landfill or another thing. And during the data retrieval, there are also some components that we gathered through this table, and we had their description here. And also there was some assumption that the author made, and there was like variables like PL and PLS are valued like $200 per day, and the mixed waste is processed through 4 sorting stage. I mean, the MCA must be 4, and the 2 sorting stage for source separated waste is 2, and also a minimal landfill diversion target, which is like a really important component. It must be like 20%, and it was like a sum like 20%. And after that, we gathered the tables of the articles, and the first table refers to their prices of the recovered materials, and the second one is about the inflow rates of components, and the table 3 is about the recovery efficiency of the components, which has like a mixed waste and also the separated source. And for the fourth table is about the sorting labor efficiency of components, and it has the same idea of the mix and also source separated. And for the equation 1, I should say that the CF was assumed to be 0 because it has the same function if it has value or it doesn't have any value. And as you can see, there are the other variables that I described in the table. And in the second equation, it has the dt, which refers to the another variable is like the daily quantity of waste disposed to a landfill.
Hello, I'm Aalok Kafle. Let me continue with the next part in our model formulation process. So after we have our objective function to minimize the cost and our first constraint regarding the waste quantity remaining for the landfill disposal, our constraint 2 here is for the total diversion of the entering waste from the mixed part and the source separated part. So this equation with TMI is source part and this is for TSI, basically saying summing up all the values for the mixed and source separated. So another constraint here is whatever is coming out of the let's say first stage should be an input for the next stage, right? And whatever is the input for the first stage is already given to us as a total input for that stage. So these are the equations that is amplifying that into an equation format so that we can put into the objective in our model. So in this part is the removal efficiency after each state, how much is being removed. So here the blue highlighted is the part that we changed from the paper itself since we found they mistyped it. And in constraint 6, this is about the labor, quantity of labor being used and their labor efficiency. That should be greater than 0, and the labor efficiency also depending upon the efficiency at different stages for different materials represented by dki, and similarly labor efficiency, number of labors lk and lski for two different stages, either mixed or so separated, should of course be greater than 0. So we change this from the paper from less than sign to greater than sign. And this is the last second last constraint we have, where this is the sum of all the materials should be di plus dt. Makes sense, that sums up to 1000 tons. And constraint 8 here is we are given that at least 20% should go to the disposal side, so we are representing that in terms of the equation format. So all these equations were basically then converted into a CSV file with coefficients for each parameter under each equation. So we ended up having 162 decision variables and 211 constraints. That's the rows. And we arranged the RHS values for each of these equations and the direction in the CSV file itself, and ran the model for PLF equals to 60 tons, being price of getting it into the landfill disposal site is $60.
So the linear programming model that was developed for reproducing this research work produced results that are consistent with the results of the original research. So the programming model was initially constrained to have a waste amount of 1,000 tons per day solid waste in the facility. And also the landfill disposal price was set at 60 tons, $60 per ton. And so having identified all the decision variables that are necessary for operating the facility, the linear programming developed values for each of those decision variables. And so part of the results that was generated show that there is almost a linear correlation between the total cost of operating the facility and the landfill disposal price. Also, it was interesting to observe that prices that are about $30 at prices that are about $30 per ton, it became desirable to dispose about half of the disposals within the facility, and at prices that are more than $100 per ton, it is feasible to dispose about 75% of the total waste within the facility, meaning that retaining just about 25% is adequate.